Hey folks, today we're going to look at 2.5 day 1, which talks about exponential function context and data modeling. For our warm-up, we have an example of a exponential function question on the multiple choice section of the AP exam. It says the exponential function f is defined by f of x equals a times b to the x power, where a and b are positive constants. The table gives values of f of x at selected values of x. Which of the following statements is true? And looking at our multiple choice options, the first half of each statement is describing function f as either an exponential decay or growth scenario, and then the second half of each option is explaining why. So before we kind of analyze which option is correct, let's think about what our exponential function would look like based off of our data. So a, remember, is going to be our initial value when x is equal to 0. What is f of x? From our table, we see that when x is 0, f of x is 40, so that means our a value is going to be 40. That's like your initial value or starting value. B is our common ratio. So this describes the change in our output values along our table. So if we analyze our common ratio by looking at how our y values change over time, remember we're looking for a ratio, a proportion value, we find that our y values are decreasing by a factor of 1/2 each time. So that means our b value is going to be 1/2. So my exponential function would be f of x equals 40 times 1/2 to the power of x. I know that this is representing exponential decay for a couple of reasons. First, in looking at my y values, I see that those y values are getting smaller or closer to 0. And then from the equation, I can see that our base value is between 0 and 1. So the correct option here would be option A. Function f demonstrates exponential decay because a is positive and b is between 0 and 1. So in this slide, we have kind of a recap of what we know about exponential functions, and we've already talked about a few of them in the warm-up. Our coefficient out in front of our exponential function, we usually refer to as a, which is going to be the initial value or the y-intercept. So on our graph here, we could look for a along that y-axis. It would be the output value when x is 0. B is the common ratio, that base value that's raised to an exponent. That will tell us whether our function is increasing or decreasing, whether we have a growth or decay scenario. And when we're analyzing tables, we are looking for that common ratio and how those output values change. We would say that the output values are all proportional to each other, or they are changing proportionally. So quickly looking at another table example here, we see that our output values are increasing by a factor of 3. They have a common ratio of 3, so we would say that those output values change proportionally. So when we are given a context or a situation, we're going to be looking for whether our output values change proportionally or not. We can say that a scenario can be modeled by an exponential function if there is a common ratio between these consecutive output values. All right, so we're going to look at a couple examples here with some context and data. We're going to determine whether or not each scenario would be best modeled by an exponential function or not by looking to see if these outputs are proportional. So in our first example here, we have a small tech startup has been collecting data on its user base over the past 3 years. Here are the number of active users they have had at the end of each year. So we can see our years are consecutive, years 1, 2, and 3, and we have the output, the number of users each year. We're going to calculate what the ratios are, the change in number of users as a proportion, and see if the ratio stays consistent or not. So looking from year 1 to year 2, we go from 500 to 950 users. Remember, if the ratio is not obvious, you can always find it by taking one output divided by the previous output. So if we take 950 divided by 500, we find that the common ratio is 1.9. So almost doubling, not quite. Now looking at the next two outputs from year 2 to year 3, this ratio will determine whether or not an exponential function is a good fit. If we get the same common ratio between year 2 and year 3, exponential will be a good model for us. So looking at this common ratio, we would take 1,800 divided by 950, year 3 divided by year 2. We find that it is close, but not exactly the same. 1.895 would be that ratio. So is an exponential model a good model for this? We would say no. And our argument would be because these outputs are not proportional or because there is not a common ratio. Here's a second scenario that I think you could try on your own if you'd like. Example 2 here is talking about Lego's new product. The Lego company is trying to produce a new line of toys for teenagers. They start small by marketing this toy only in the city of Minnetonka. Here are the number of units sold after the first 3 months of sales. Is the company's sales growth over time exponential? Why or why not? If you'd like, pause the video, give it a try, and press play when you're ready to check your answer. So we want to check the ratio of units sold over time. So looking from month 1 to month 2, that ratio would be 300 over 200, which simplifies to 3/2 or 1.5. Looking from month 2 to 3, our ratio would be 450 over 300, which would also simplify to 3/2, meaning that those output values are proportional because we can find a common ratio. So our answer here would be yes, an exponential model would be good for this scenario because the output values are proportional. All right, next we're going to talk about a number E, also called Euler's number. E is a special mathematical constant that's approximately equal to 2.71828. So similar to pi, it is irrational. It's called Euler's number, pronounced like oil, Euler. Euler is a person that is credited with kind of bringing in this number when we talk about exponential scenarios. So it's irrational, it goes on forever without repeating, and it shows up a ton in applications of exponential growth, including finance, economics, physics, and engineering. So we have a couple formulas that we can use when talking about interest, talking about money in your bank account growing over time. There's two different ways that we can calculate the interest. The first one is calculating interest that's compounded on specific time intervals. That's going to be the first one, versus when our interest is compounded continually or calculated continuously. You notice here in that second function, we have an exponential expression with a base of e, this Euler's number or Euler's constant. So in the case of calculating interest that's compounded on a set time basis, this first one, you have the initial amount, P sub 0, it's called the principal. You have the rate, R, always represented as a decimal, even though it's communicated as a percentage. In our formula, we'll convert it to a decimal. We have N, which is going to be the number of times that interest is calculated per year. So if it's calculated every month, n would be 12, for example. You'll see n again in the exponent, and then t, our amount of time, is going to be number of years. With this second formula, you'll notice many of the same variables. You have the principal and you have the rate. Notice that the rate is now moved into the exponent position, and there's no n because we're calculating this interest continuously. It's not a set number of times per year, but constantly. And then t is still going to be our time in years, where r is our yearly rate. So to practice these two, we're going to look at a scenario where we deposit the same amount of money into an account for the same amount of years, but our interest is going to be calculated differently. Our scenario here says, on the day of a child's birth, a deposit of $25,000 is made in a trust fund that pays 8.75% interest. Determine the balance in the account on the child's 25th birthday if the interest is compounded weekly, monthly, and continuously. So a few things are going to stay the same regardless of how often this interest is compounded. Firstly, the principal is going to stay the same. That's the initial amount, $25,000, as well as the interest rate. As a decimal, that would be 0.0875. The other thing is going to be time. We're going to be looking at 25 years in the future. So starting with weekly, that's a specific time interval. We're going to be looking at that first formula, and n is going to be 52. As there's 52 weeks in a year, so it would be calculated 52 times over the course of the year. Our function would look like this. P of t is equal to 25,000 times 1 plus 0.0875 over 52 to the power of 52t. Now this is definitely not a function that's reasonable to work with without a calculator. So using a calculator, we would plug in an input of 25 to represent the 25 years that are passing, and find that our account has $222,413.32. Switching that now to a monthly basis, our interest compounded monthly, we're still going to use that first formula, but now n is going to be 12, since there are 12 months in a year. So our function is going to look almost exactly the same, but n in both places is going to be replaced with 12. Using a calculator to help us, we'd plug in 25 and find that there would be $221,061.10. So not as good as the weekly basis. When we calculate this interest compounded continuously, that's when we're going to use this next one with E, Euler's number. Our function would be this principal, 25,000, times e to the power of r, 0.0875 t. Plugging in 25 as our input, we'll find that this last scenario actually produces the most money, $222,822.57. We can use this new formula of growth that's happening continuously to look at other contexts that don't involve money, like this example here. It says the number of bacteria in a certain population increases according to a continuous exponential growth model at a rate of 8.1% per hour. There are 1,800 bacteria at time 0. It says find how many bacteria are present after 7 hours. So you'll notice that the time that we're looking for in hours matches the rate is an hourly rate. So that rate as a decimal would be 0.081. The time would be 8 hours, and then our initial value, then initial population is 1,800. So to find what that population is going to be in 7 hours, we would take that initial value, 1,800, times E, since it's a continuous growth, to the power of 0.081 times 7. Okay, using a calculator to help us simplify, if you plug that in, you should get 3,173.346. All right, in our last example, we're going to bring back some skills from earlier in Unit 2 and even Unit 1. It says the number of bacteria B in a particular culture can be modeled by the exponential function below, where T is measured in hours. So we have this function B of T is equal to 17 times E to the power of 0.31 T. It says let the function below be an equivalent expression for B of T. Find the values of A and B. So you'll notice that in the expression we're being asked to write, T is by itself in the exponent. So essentially we want to get rid of this dilation, this horizontal dilation that's within the function that's given to us. In 2.4, we practice this using our properties of exponents. So what we want to do is we want to take the function above and rewrite that base as e to the 0.31 power raised to the power of t. And now we're going to be able to simplify this base with the help of a calculator. E to the 0.31 power, if I type that in, is going to simplify to a decimal expression 1.363. So rewritten without that horizontal dilation or that coefficient in the exponent position, we'd have 17 times 1.363 to the power of t. You'll notice that the A value, the initial value, does not change, just the base value does. So A stayed 17, that initial value, but our base changed to a new base ratio of 1.363. Part B is bringing back an old friend, our average rate of change. It says find the average rate of change of this original function b of t over the interval t equals 1 and t equals 7 hours. So we're looking for this slope between hour 7 and hour 1. So we're going to take the change in output over the change in input. We'll use a calculator to help us with these output values. At hour 7, it looks like we have an output of 148.891. At hour 1, we have an output of 23.178. And then we'll divide that by 6, 7 minus 1. So if I use a calculator to help me simplify that numerator, we get 125.713. Divide that by 6 to find the average rate of change on that interval, which is going to be 20.952. Last one here, it says find a value of t when the number of bacteria in the particular culture is 1,000 exactly. So we're trying to solve where b of t is equal to 1,000. Okay. Right now we don't have a way to algebraically solve this. We will soon when we talk about logarithms, but until then we are going to use the graphing feature on our calculator. We're going to graph this function b of t, this exponential function, and then we're also going to graph the line y equals 1,000. So our exponential function is exponential growth. We can see that base was bigger than 1. And then we will graph the line y equals 1,000 and find that intersection. So we can find where on our function we have an output of 1,000. So go ahead and type that into your calculator. I'm going to do the same. You'll have to zoom out since that y value is quite large. And I'm finding my intersection is at 13.144, comma 1,000, which means that our time would be 13.144 hours. That's the end of 2.5 day 1. Go ahead and give your homework a try and write down any questions you have.